Burn like a pro.
In chemistry, some of the most important ingredients are completely invisible. We're talking, of course, about gases. Today, we're going to pull back the curtain and show you exactly how to capture and purify these tricky substances, turning something you can't see into something you can understand. So let's just start with the biggest question right off the bat. How in the world do you capture something you can't even see? It sounds a little like a magic trick, doesn't it? But it's not magic. It's just really cool science. And it all comes down to understanding two little secret rules of the invisible world. And here they are, our two golden rules. It's all about asking two simple questions. First, is our gas heavier or lighter than air? That's its density. And second, will it dissolve in water? That's its solubility. You get the answers to these two things, and you've pretty much cracked the code. All right, let's put this into practice. Take a look at this decision tree. Think of this as our roadmap. By just following the path based on those two properties, solubility and density, this chart will point us to the perfect collection method every single time. So let's walk through it. So following our little map here, the first question we always ask is about water. Does our gas dissolve in it? If the answer is no, or maybe even just a little bit, then our job just got a whole lot easier. The path forward is really simple and direct. And here's that method in action. It's called displacement of water. As you can see, we just bubble the gas through water into a tube that's already full of water. The gas rises, pushes the water out, and gets trapped right at the top. Simple. But here's the really important part. This is the only way to collect a gas like oxygen because its density is almost exactly the same as air. But what if our gas loves water? It dissolves right into it? Well, then that whole water displacement method is completely off the table. So now we have to rely entirely on our second rule, density. Is our gas heavier than air, or is it lighter? Okay, so if our gas is denser, heavier than air, like carbon dioxide, we use this simple and kind of elegant technique called downward delivery. We literally just feed the gas into a regular upright container. Because the gas is heavy, it sinks to the bottom and forces all that lighter air up and out. Gravity is doing all the work for us. And what if our gas is less dense than air, like ammonia? Well, you probably already guessed it. We just flip the whole thing upside down. This is called upward delivery. The light gas just floats up into the inverted tube, pushing the heavier air down and out the bottom. It's the same exact logic, just, in reverse. Okay, so we've collected our gas. Mission accomplished, right? We can go home? Not quite. There's a hidden problem. Our gas is almost always wet, meaning it's full of water vapor. And for an experiment to work right, you need a pure sample. That means there's one final step. We have to dry it. To dry our gas, we pass it through a special drying agent. You can see our three main options here. Fused calcium chloride, which is basically a type of salt, concentrated sulfuric acid, and calcium oxide, which you might know as quicklime. They're all great at soaking up moisture, but you gotta notice the warning symbol here. Choosing the wrong one won't just fail. It can completely destroy your entire sample. This brings us to the single most important rule of gas purification. I like to call it the golden rule, and it's right here. Match acid with acid and base with base. So, if your gas is acidic, you need an acidic or neutral drying agent. If your gas is alkaline or basic, you need a basic or neutral one. Mixing them up is just a recipe for disaster. So why is this so critical? Well, it's because of something called the neutralization hazard. Just look at the diagram. If you try to dry a basic gas like ammonia with a strong acid like sulfuric acid, they don't just sit there peacefully. They react with each other, sometimes pretty violently, and your precious gas sample is completely destroyed. It's basically a chemical cancellation. This compatibility grid is your safety net. It makes it really easy. As it shows, if you have an acidic gas, concentrated sulfuric acid is your go-to. For a basic gas, you're going to want to use calcium oxide. And fused calcium chloride is a great neutral option, but, and this is a big but, it actually reacts with ammonia, so you never use them together. This grid is your guide for sure. So let's put it all together with the ultimate cheat sheet. Just take a second to look at this. For collection, it all comes down to density and solubility. Heavy gases get downward delivery, light gases get upward delivery, and those insoluble ones get the water displacement method. And for purification, the number one rule is to avoid that neutralization reaction. Everything you need to remember is right here. So we started with a totally invisible problem, and we found the solution just by understanding a few simple invisible rules. It really makes you think, doesn't it? What other unseen forces are out there shaping our world, from the lab to the entire cosmos, just waiting for us to figure out the rules of the game?